Today's presentation deals with anesthesia and electrical safety, and this presentation is based on the presentation given at the recent Cleveland Clinic Foundation Anesthesiology Review course. I can think of few topics as boring as anesthesia and electrical safety, and yet this particular talk, paradoxically, was awarded the highest level of ranking of all the talks given, suggesting that it fills a niche in solving people's problem in understanding this concept from the point of view of preparation for the written and oral boards. So I have edited this presentation slightly from the previous version of it given at that review course in April and May. And at the end, if you have any questions of any kind, please let me know. The outline is to cover the principles of electricity, the concept of electrical shock, the distinction between macroshock and microshock, the concept of grounding, the use of the ground fault circuit interrupter, the use of the line isolation monitor, and some comments on electrocautery. In addition, here I have grayed out electromagnetic interference and implanted defibrillators, which, while important topics in dealing with electrical safety, are beyond the scope of this presentation, and they could fill other presentations as well. For example, in the case of implanted defibrillators, a whole half-hour to hour presentation could easily be done. Let's start off with a presentation of electrical principles done at the grade 9 level so that everyone is easily on board. First, remember that electricity is the flow of electrons, and that any substance that permits the flow of electrons or electrical current is called a conductor. Any substance that does not allow the flow of electrons or current is called an electrical insulator. And on the bottom right here, we have a typical electrical insulator used in the past in rural America that would be used to supply houses. And you may remember as a kid people trying to shoot these things with their .22 caliber rifles as a form of vandalism. These are not as commonly used in the past, and some people collect them, but they're electrical insulators. So remembering that electricity is electron flow, when the electrons flow in only one direction, that's direct current. But the current that we get from the wall, the mains, it switches direction at regular intervals, 120 times per second for 60 hertz wall current, which undergoes 60 cycles per second. But because in one cycle it goes one way and then back the other way, it switches 120 times per second. In Europe, the voltage is typically at 50 hertz, whereas for us it's typically 60 hertz. And in some avionics equipment, to keep the size of the transformer down, it's typically 400 hertz. Now here is an animation on the left showing the concept of direct current from a battery. And what we see is the electrons flow from the negative terminal through an ammeter driving, for example, an electrical light bulb, and the electrons return to the positive terminal. So the electrons flow in one current only, and the animation on this is shown on the left-hand side. Another way of viewing this that is conceptually more complicated is not to talk about the flow of electrons, but to talk about the flow of conventional current, in which case then the current would go from the positive terminal of the battery through the light bulb, through the ammeter, to the negative terminal, and that's the concept of conventional current, as opposed to the concept of electrons flowing. And at this stage, I would recommend you think in terms of the concept of electrons flowing, but engineers talk about the very opposite, the concept of conventional current. And this can be a source of confusion and even disaster when building equipment if you don't understand this distinction. Now, by contrast to DC current, alternating current switches paths 120 times per second, as I've said, in the case of ordinary 60 hertz current. And this current is generated by electrical dynamos as illustrated in the animation on the bottom right. That is, that by putting a loop of wire or many loops of wire through two magnets as configured in the illustration, you can generate electrical current in this manner. And of course, the speed at which the dynamo rotates influences the frequency of the current. And since we want 60 hertz current, it's very important that the matched rotational frequency occur to make sure that the 60 hertz is correct. In some cities, the 60 hertz is so accurate that you can run your clocks by it, whereas in other locations, the 60 hertz is only nominally 60 hertz and may vary by a considerable amount. You can't use it for clock purposes. That's more academic these days now that you can get atomic clocks, which are accurate up to 1 second a century. But in the past, this used to be used in some places for driving the clock systems. Now let's move on to talk about the concepts of current, voltage, resistance, and power, which are illustrated schematically in this diagram, showing that if there is a voltage placed across a resistance, current will pass through it, and as a result, work will be done and energy will be released. We use V as the voltage, sometimes E as voltage, meaning electromotive force. We use I to denote current, R for resistance, and W for energy or work. This is illustrated in terms of a simple mathematical relationship, Ohm's law, where V equals I times R, where V is electromotive force, again in volts, I is the current in amperes, R the resistance in ohms. All of these, of course, are named after individuals. Volts after Volta, the Italian physicist, amp after amperes, the French physicist, and ohms after Ohm, the German physicist. Ohm's law, then, is simply V equals I times R, or if you prefer to use E for electromotive force, as many authors do, E equals I times R, or voltage equals current times resistance. It's interesting that we're familiar with Ohm's law in terms of fluids in the same way, because we remember that pressure equals flow times resistance, or flow equals pressure divided by resistance, and we use this all the time when we are calculating things like flow in hemodynamic measurements or pressure in hemodynamic assessment. Well, let's take an example to make this concrete. What resistance across a 100-volt source would produce a current of 100 milliamps, or 0.1 amperes? Well, from Ohm's law, we know that R equals E divided by I, so that will be 100 volts divided by 0.1 amps, or a resistance of 1,000 ohms, or 1 kilo ohm, across a 100-volt source would produce a current of 100 milliamps. This is an important number to remember because 100 milliamps through the body is enough to induce ventricular fibrillation if the current path goes through the heart. That would be called macroshock, something we'll introduce you to in a minute. Well, the analogy in blood pressure is that blood pressure equals cardiac output times systemic vascular resistance. So blood pressure is equal to the cardiac output times SVR, and this is an analogy that can be used to understand the concept of flow, pressure, and resistance. Another concept is electrical power, sometimes denoted by P or sometimes by W, and it's measured in watts. And the watts, or the power, is equal to E, the voltage, times the current. Again, this is all grade 9 or grade 10 physics that you're all pretty familiar with. Those of you who don't like to derive things from first principles can refer to a chart such as this one to just figure out what the relationships are without knowing any algebra at all, even though the algebraic requirements for this are things that you would find trivial when you were in high school. So any relationship between voltage, watts, amps, and ohms can easily be determined through a schematic of this kind. Well, electrical energy is a watt-second, and also that's known as a joule, and it's a common designation for electrical energy expended in doing work. The energy produced by a defibrillator is measured in watt-seconds, or joules, and the kilowatt hour is frequently used to measure larger quantities of electrical energy, such as you use every day in your home. So, for example, electrical utility companies charge their customers on the basis of kilowatt hours of electricity consumed, whereas in the case of a defibrillator, the amount of energy consumed that's delivered to the heart is much smaller, for example, 200 joules or 200 watt-seconds. Another concept that comes up in the discussion of electrical safety is the capacitor, and it is a device that stores charge, or electrons. A capacitor consists of any two parallel conductors that are separated by an insulator, sometimes known as a dielectric. And in contrast to DC circuits, a capacitor in an AC circuit permits some current flow, depending on what's called the impedance of the circuit. So even though these two plates are separated by a dielectric, and if measured with an ohm meter would read infinite ohms, they do pass alternating current because they have what's called a non-zero impedance. The importance of this shows up as stray capacitance in electrical circuitry. Because stray capacitance, also known as capacitive coupling, is inherent in all electrical equipment by virtue of two wires being close to each other. It's a generally undesirable component, and it's not designed into the equipment, but is incidental to the equipment construction. And while it is possible to minimize stray capacitance by careful design, unfortunately, this problem exists in all electrical equipment and has to be dealt with. And we do have some ways of dealing with it, we'll discuss in a minute. Let's move on now to talk about electrical shock hazards, because people become injured or death occurs when voltage pushes electrons through the human body, particularly through the heart. This can result in electrical burns or in ventricular fibrillation. So if electrical systems are not properly wired, people can become electrocuted. Electrocution by DC current tends to be less dangerous than electrocution by alternating current at 60 hertz. But fortunately, high-frequency current, such as you get with electrocautery, has low tissue penetration and does not excite contractile cells, but can still cause burns, as you know in the operating room. It's interesting that in the early days of electricity, DC was proposed by Edison as a means of providing electricity to the communities, whereas AC was proposed by Westinghouse as a means of providing electricity to the nation. And it wasn't clear then which was the best way of promoting electricity. But the evidence was mounting that AC was more practical, and Edison was upset over this and wanted to see if there was a way that he could ensure that people got a bad taste for AC. And he pointed out that if you designed an electric chair, it would have to be done with AC. And he proposed that just like in France during the Revolution when they chopped off your head, it was named after Dr. Guillotine who invented it. He suggested the electric chair be called the Westinghouse chair. It never stuck, but he did try to give alternating current a bad name because of its propensity to cause electrical shock hazards. It turned out that Edison was wrong. We do distribute electricity by the AC route. He got a lot of other things wrong. He thought that the way to promote the phonograph was to use cylindrical rolls, whereas everyone knows now it was done on vinyl. But he got a lot of things right, and so he is truly America's greatest inventor. Now let's take a look at electricity that comes out of the wall, the mains electricity. In a typical AC circuit, there's a potential difference of 120 volts between the hot and neutral sides of the circuit. As current flows through a resistance, which in AC circuits is more accurately called impedance, because we're talking about alternating current, it then passes through the circuit and returns to the electrical power company. And this is taken from Barash's textbook, which has an excellent chapter on this that I would suggest you all review before your boards. Now, an individual can complete an electric circuit and receive a shock by coming in contact with the hot side of the circuit at point A. This is because he or she is standing on the ground, designated point B in this diagram, and the contact point A and the ground point B provide two contact points necessary for a completed circuit. The severity of the shock that the individual receives is dependent on his or her skin resistance, which could be as little as 1,000 ohms under clinically desirable or undesirable circumstances, depending on how you look at it. This raises the notion of electrical shock, which comes into two flavors, macroshock and microshock. Macroshock is large electrical currents that can cause harm, whereas microshock are small electrical currents that are dangerous only to susceptible individuals. For example, patients that have pacing wires in the heart, or patients that might have a central line going into the heart. So microshock usually involves exposure to the patient by virtue of special circumstances with a catheter or electrical pacing wire going directly into the heart. This diagram taken from Barash's textbook shows you the distinction between microshock and macroshock and shows you the various effects at the macroshock and microshock level. 1 milliamp of macroshock is 1 milliamp of current here involves the threshold of perception, that at around 1 milliamp of electrical current at 60 hertz, about 50% of people can feel it and 50% of people can't. And that's the concept of the threshold of perception. At 5 milliamps, this is accepted as the maximum harmless current intensity that can occur. Between 10 and 20 milliamps, this is the let-go current before sustained muscle contraction occurs. That is, you get sustained muscle contraction, but it's not so strong that you can't let go of the wire if it induces muscular contraction. At 50 milliamps, you get pain, possible fainting, mechanical injury, and the heart and respiratory functions continue. So the heart can still tolerate this, and respiratory function still occurs. But above 100 milliamps of macro current, ventricular fibrillation can start. And it says here that respiratory center remains intact. But I assure you that respiration will cease shortly after ventricular fibrillation sets in. At 6,000 milliamps, you have sustained myocardial contraction followed by a normal heart rhythm, temporary respiratory paralysis. Burns occur if the current density is high. And 6 amps is an enormous amount of current to go through anybody. By contrast, in the microshock setting, as little as 100 microamps, or 0.1 milliamps, through the heart will induce ventricular fibrillation. And 10 microamps is recommended as the maximum 60 hertz leakage current that would go through a person in the microshock setting. So just to emphasize this, if the 60 hertz current is under 1 milliamp, it's basically imperceptible. At 10 milliamps, you get effect on the skeletal muscle, but you can easily let go. And ventricular fibrillation can be induced with as little as 100 milliamps of macroshock through the heart, or 100 microamps of microshock current going through the heart in the case of a person who might have a pacemaker wire placed or a central line placed. So I would emphasize this particular 100 microamp microshock causing ventricular fibrillation and 10 microamps as the recommended maximum leakage current for those people who are preparing for the boards, because this is the kind of thing they love to ask. So again, the maximum leakage current allowed in electrical equipment in the operating room is 10 microamps. That also explains an anomaly that many of you have observed over time, is that the wires in some of this electrical equipment are very short. And you say, well, why do they make the wires so short when I've got to move the equipment over to plug it into the wall? Why not have longer wires? And the answer is because the manufacturer wants to keep the leakage current down, and the way they do it is keeping the wires to plug in the wall very short. Of course, then you have to add an extension, and then that's potentially a problem, but it's not the manufacturer's problem, it's your problem. And so it allows them to get by regulatory authorities with relative ease. Okay, let's move on to talk about electrical grounding. In your house, you probably have 3-pronged plugs, and these are grounded plugs, but you may have visited houses, some older houses, where they have 2-pronged plugs and no ground. So modern homes have a 3-pronged grounded system to reduce the chance of shock. And this is to prevent shock hazards such as those illustrated in the diagram on the right, or you have a lady listening to a radio with her curling iron plugged in with the basin here filled with water, and she's drying her hair with an electrical hair dryer. And these are all potential sources of electrical shock hazards that grounding can help ameliorate. In the outlet in your house, there is a round prong receptacle, and it connects directly to the ground and is not part of the normal current flow path, which we'll illustrate in more detail in a moment. So we have a neutral and a hot, and these are sort of rectangular prongs, and then we have the ground, which is a circular prong. And you see this every day when you plug in your stuff. In the hospital, we're concerned about the quality of these plugs, and so they're inspectable in some way. Panel A shows a hospital-grade plug that can be visually inspected, and the arrow points to the equipment ground wire whose integrity can be readily verified by visual inspection. B shows a hospital-grade plug that can be easily disassembled for inspection. And note that the prong for the ground wire, shown with an arrow, is longer than the hot or neutral prong, so it is the first to enter the receptacle to help establish safety right on. And in panel C, the arrow points to the green dot denoting a hospital-grade power outlet, which many of you have seen. You may have also seen red power outlets. Those are the ones which are hooked up to emergency power, and should the distribution of power fail for the city, the concept is that there will be a diesel generator or other source of energy start up almost immediately and supply power to those outlets. So why is our electrical equipment grounded? Well, here are some of the reasons. You can have stray or broken wires which go to the equipment case, causing a fault. More about that in a minute. We also read about stray capacitance and capacitive coupling. So equipment ground wires are attached to the case of an instrument to allow stray currents to have a low resistance path to ground and reduce the risk of macroshock, which we'll show you in a minute. Here is a typical old house with an ungrounded two-prong plug. And imagine for a moment that the hot wire on that two-pronged plug is frayed and therefore touches the metal case on the instrument this person is using. It might be, for example, a radio or a hairdryer. Then if the individual touches the metal case, which has to it a short circuit to the hot outlet, what will happen is that when he touches the hot case, electrical current will go through him to the ground where he is standing on. And electrical current passes through him. If it's over 100 milliamps of current, he's at risk of ventricular fibrillation. So let's see how a three-prong plug gets around that. If we have a grounded three-prong plug, then if there is a short circuit from the hot wire to the case, that case being grounded means that all of that electricity goes through the ground wire, and what will happen is a circuit breaker will blow, or if that doesn't happen, if he touches the ground, he has much higher resistance. If he touches the hot case, it has much higher resistance going through him, say 1,000 ohms, than through the three-pronged plug, say 1 ohm or less, and so he's safe from electrical shock. In the real world, the most likely thing that would happen in this scenario is that you would get a circuit breaker blowing. This is illustrated here one more time. Suppose that this individual with his drill has a broken terminal, and suppose in addition there is a line to ground fault in his drill so that the metal casing of the drill is directly connected now through a frayed wire to the hot part of the case, to the metal part of the case, and from there to the hot wire on the outlet. Then if there is a broken terminal, the electricity will go through him rather than through the ground wire, which is broken. To do the analysis of this, if he has 1,000 ohms of resistance and there's 120 volts of electricity going through 1,000 ohms, the current under Ohm's law is E equals IR, or I equals E over R, or the current is 120 volts divided by 1,000 ohms. That's 120 milliamps, and that's enough to induce ventricular fibrillation. That's why if you're going to do this kind of thing, you want to make sure your buddy's nearby. You can dial 911 and rescue you. Okay, let's talk now about ground fault circuit interrupters, which many of you have in your home. Electrical codes for most new construction require that ground fault circuit interrupter circuits be present in potentially hazardous, such as wet areas like bathrooms, kitchens, or outdoor electrical outlets. And you'll see them in many of the restrooms at the Cleveland Clinic. Ordinarily, the current in both the hot and neutral wires in a power outlet is equal. It goes out the hot, turns through the neutral, and nothing goes through the ground. The ground fault circuit interrupter monitors both sides of the circuit for equality of current flow, and if a difference is detected, the power is immediately interrupted. If an individual should contact a faulty piece of equipment, such that the current flowed through the individual, an imbalance between two sides of the circuit would be created, which would be detected by the ground fault interrupter circuit. The disadvantage of using a ground fault interrupter circuit in the operating room is that it interrupts the power without warning. A defective piece of equipment could no longer be used, which might be a problem if it were of a life support nature, like a ventilator or like a cardiopulmonary bypass machine. Whereas if the same faulty piece of equipment were plugged into an isolated power system, the line isolation monitor would alarm, but the equipment could still be used. And this explains why line isolation monitors and line isolation techniques are commonly used in the operating room, and we'll be talking about that in a little bit. But just to close up with ground fault interrupters, here is the schematic diagram showing the nature of ground fault interrupters and their design. And if there is equal current flowing from the hot wire to the return path, then there is a comparator circuit which says that if there's no difference between the two, the comparator circuit is inactive and nothing happens. But if there is unequal currents, then the sensor coil activates a circuit to discontinue or disconnect the electrical device, and it's no longer operational. It's like a relay that goes to the open state, or a solenoid that goes to the open state, and then the electrical circuit is interrupted, and that's the end of it. Of course, that is a problem, as I said, for some life support equipment, which is why we use line isolation techniques. So let's move on to line isolation monitors and line isolation techniques. In many operating rooms and intensive care units, we utilize what's called an isolation transformer to isolate our equipment from the primary source of power, the 110 volts that we get from the electrical power company. So on the left here, you can see that the electricity you get from the power company has a voltage difference between hot and neutral of 120 volts, but also a voltage difference between the hot and ground of 120 volts. And you can get an electrical shock by having one finger in the hot wire and one finger on the neutral wire, or alternately one finger on the hot wire and one finger on ground. But on the right-hand side, we show that with an electrical isolation transformer, while there is 120 volts between line 1 and line 2, and notice we don't call them hot and neutral anymore because by virtue of isolation, this nomenclature is no longer meaningful. While we have 120 volts between line 1 and line 2, we have no voltage difference between line 1 and ground or between line 2 and ground. And if you're on the ground, in a pool of saline, for example, and you touch line 1, nothing will happen, or if you touch line 2, nothing will happen, and you're isolated, and this offers a safety feature. So there's no direct connection from line 1 and line 2 to ground. So this can be advantageous. But what we have to make sure is that the line isolation transformer itself works well, because capacitive coupling and stray wires can still be a problem in the real world. So we want to look at the quality of that isolation, and that is called a line isolation monitor. Just to go back to emphasize this point, in a conventional circuit, an individual can complete an electrical circuit and receive a shock by coming in contact with the hot side of the circuit at point A, and this is because he or she is standing on the ground, and the contact point A and the ground point B provide two contact points necessary for a completed circuit. And the shock that you get will depend on the resistance in the pathway going through the patient's heart. But with a line isolation transformer, if the patient or the individual, the clinician, is standing on the ground, even in a pool of saline, if he or she touches line 1, there's no current flow to ground, or touches line 2, there's no current flow to ground, as long as the isolation transformer works perfectly. But being a real-world component, they're not perfect, they're just almost perfect. We need to monitor their performance, and the line isolation transformer monitors the performance of the isolation transformer. So this means that the power source is isolated. It provides protection from macroshock, but as we'll see in a while, not from microshock, and I'll explain that in a minute. And faulty equipment plugged into an isolated power system does not present a shock hazard, because even if you touch one of those wires, very little current passes through you. So the line isolation monitor, distinct from the line isolation transformer, monitors the quality of the line isolation transformer. It continuously monitors the potential for current flow from the isolated power supply to ground. It determines the degree of isolation between the two power lines and the ground and predicts the current flow that would occur if a fault did occur. So the line isolation monitor is shown in the schematic here, where it monitors the current that would flow between line 1 and ground and line 2 and ground if a fault were to occur, such as the short circuit shown on the right-hand side. And typically, what we want is to keep that current under 2 to 5 milliamps, which we'll explain in a minute. So a line isolation monitor alarm indicates the existence of a single problem, a single fault, that an ungrounded system is being grounded, that you're back to the regular power situation in this case. There's no longer isolation, but there's still no chance for a shock in this case because you're back to the original grounded system should this kind of single fault condition occur. A second problem, or two faults, are necessary for a shock to occur in this setting, and you need a faulty piece of equipment plus a problem with the line isolation monitor, and you need an unsafe environment like an electrical device problem plus you being in a pool of normal saline. So a single fault condition with a line isolation system is okay because you're not going to get electrocuted, but it warns you that you could potentially have a problem. The line isolation monitor alarm goes off if you have more than 2 to 5 milliamps of current flow being detected. But remember the macroshock versus microshock distinction? 2 to 5 milliamps of current going through you in a macroshock setting is harmless. But in the microshock setting, still can be a problem. And so the line isolation monitor doesn't solve the problem of microshocks, but does help with the problem of macroshocks. So remember, the line isolation monitor does not protect against microshocks since it detects 2 to 5 milliamps of leakage current. So the line isolation monitor does not protect from microshock, but it does warn of a potential problem. And one common board exam question is, what do you do if the line isolation monitor goes off? And the best thing to do is remove the last piece of equipment that was plugged in that may have enough leakage current to trigger this. And you can plug it in a different outlet or simply use a different piece of equipment. And then you want to call the engineers to get it fixed. Now, in some hospitals, the line isolation monitors are not owned by biomedical engineering. They're owned by physical plant. In other hospitals, they're the domain of biomedical engineering, and you got to figure out which is which when you have a problem, because those two groups are separate and distinct. So, in the OR power source, it is ungrounded, and the equipment is grounded, and the line isolation monitor is used in this context. Rafi?
Dr. It doesn't mean that the last one was faulty. It means that the addition of all of these leaks together is above 2 to 5. So you might have something else before which was more faulty, and you might as well take the other one out if the last one is vital for you.
You are right in that the additional final piece of equipment might have provided the final amount of capacitive load. And you could try altering your rearrangements. The practical thing is just to unplug it and see what happens, because it may have been the biggest piece of equipment responsible. But it may be that another previous piece of equipment, as you correctly state, provided the bulk of the leakage current, and the last piece was just the last straw. That's correct. Yes?
At least in practice exams, they like that last piece of equipment that triggered the line isolation monitor to be a cardiac defibrillator in a patient who's in ventricular fibrillation. So the question is, do you have to unplug it immediately, or can you defibrillate the patient with this somewhat faulty piece of equipment while a nurse is getting you another defibrillator?
And the answer would be, obviously,
yeah, use it.
Defibrillate, because defibrillation time is myocardium. Yeah, so you want to defibrillate instantly. Let's close up by taking a look at electrocautery. And the electrocautery system involves a high frequency current coming from the electrosurgical unit, also known as a Bovie, because it was invented by Dr. Bovie. And the idea is that at the source where the electrocautery is occurring, there is a high degree of electrical current, radio frequency current, that can either cut tissue or coagulate tissue depending on the waveform. And this current passes through a return plate, and at the return plate you have low current density. And so you get burns where there's high current density, and where there's low current density you have no burns. And that's the concept of electrocautery in a nutshell. The frequency that you pick and the duty cycle of the waveform that you get will determine whether you cut or cauterize, and that's beyond the scope of this discussion. But what we emphasize here is that it's very important that the electrocautery plate, the return plate, also known as the grounding plate, although it's really a return plate, it's very important that be on the patient in a secure way so that we don't run into a problem of high current density because it's only returning through a portion of the plate. Because if that's the case, you can get electrical burns at the site of the return plate. And that's why you may notice that the operating room nurses are so careful about the quality of the return plate and that it be on an area of the body, hopefully an area that doesn't have a lot of hair. Sometimes they'll even shave the area to ensure that there's not much hair, and that can at least theoretically be useful. I do remember a story of a gentleman at Toronto General Hospital who had a lot of hair in his thigh, and the nurses shaved a big patch on the lateral aspect of his thigh to put on an electrocautery plate for what was otherwise a small procedure. And when he woke up, he saw this large area on his left leg which had no hair. And he pointed out to everyone that that put an end to his modeling career. He modeled bicycle shorts and stuff. And he was very upset because it cost him money. So that's an aspect of it that most people wouldn't have anticipated. It shows you that it's potentially a problem. Okay, I think it's probably time to answer some questions.